Section 2.3, subspaces. Starting with the definition, a subset U, subset of V, vector space, it's called a subspace of V vector space if U itself is a vector space. Under the addition and scalar multiplication of the original vector space V. So we are talking about subsets that are also subspaces. It will be important to understand that they are not the same. A subset can be not a subspace. Theorem in this section, the main theorem, is that we figure out what do we need about the subset in order this to be a subspace. The subset U of V is a subspace of V if and only if, so this is again a back and forth equivalency statement. We need three parts. First of all, it shouldn't be empty space, so U is non-empty. Then the second property is that for all U V vectors from this subset U, U plus V is also in the subset U. With other words, U is closed to addition. And the third property is that for all scalar A and for all U vector, A times U is also in the subset U, which means that U is closed to scalar multiplication. So closed means that scalar multiplication doesn't go outside. We will skip the proof. Let me tell you why this theorem is important, and the proof is very long. It's not difficult, it's just very long. You can find the proof in part in the book or many other places. The idea is that we're supposed to check all the properties of a vector space, or the defining properties. So the defining properties, the definition for a vector space had several parts. We had A, then we had properties B1, B2, B3, B4 for scalar multiplication. So these are several different things that we're supposed to check. The nice thing is that this theorem let us check for a subspace only three conditions. So that's supposed to be easier than to check the definition of a vector space. All right, let's see some examples. Again, a basic example with R2. And then let's have U as a straight line passing through the origin. Let me also mention that you should already know from undergraduate classes, and we will come back to this later, that in R2 points on vectors are considered to be equivalent. So if you have a point xy, you can also consider the vector going from the origin to this point. So when you connect the 0, 0 with the xy point, you get a vector. So when I talk about U as a straight line, you can say that this is a set of points or set of vectors. So here is V as R2, and then we consider as a subset a straight line. If we want to check that this is a subspace, this is not empty. Sure, because we have all these points. Then addition in U. So if we have vectors in U, for example, we have U and we have another vector V in the same line, that means these are parallel vectors, then you have to know how to add together vectors, that you put one to the top, to the tip of the other, you shift parallel to itself, and then you get U plus V vector, and it's also in the same line. So U plus V will be parallel to U and V, and it's in U. So it stays, addition stays in U. And then if you look at scalar multiplication, also it stays in U. How do we see that? What does it mean? For example, C times U, this is just scaling. Actually, the scalar comes from scaling. So we can check all these three conditions to see that U is a subspace of V. So this wasn't a rigorous proof. This is just a graphical sketch. It's very useful many times to visually describe what we are working with. But let me mention that this is not a proof. Yeah. So in this class we don't accept visual pictures as proofs. For rigorous proof we have to use notation and basically calculus. Rigorous proof, we have to set up notation for U, which is a line through the origin. Well, it's supposed to have a slope. Let's say that with given slope M. So the notation would be, for example, using the vector notation xy vectors, where y is m times x, and this is true for all x real number. So the xy coordinates of the line have this property that y is m times x. That m is the slope, the y-intercept is 0, that's why it goes to the origin. Another way to write this set with set theoretical notation is x mx, and then we just say that this is for all x real number. And then we have to show things like U is not empty. That means we have to show that it has at least one element. We see that x can be any real number, so let's choose on x. So for x equals to 0, we have x mx is 0, 0. It's in the set. We already, of course, knew that from the picture that 0 is an element of the line, the origin, since the line goes to the origin. That means U is not empty. Second property was that addition of vectors. So we need two vectors, V and W from U, and we have to look at V plus W. So for that we have to look at how V can look. For example, it can have x1, mx1 coordinates, and then W can have x2 and x2 coordinates for some x1, x2 real numbers. We don't know what real numbers, we don't care. Then we have to write down how the addition looks like. x1 mx1 plus x2 mx2. We already defined addition in R2 in the plane, that it goes entry by entry. So we have x1 plus x2 in the first coordinate and m times x1 plus m times x2 in the second coordinate. And of course the trick is that in the second coordinate we can factor out m. Then we see that we have x1 plus x2 both in the first component and in the second component. So if we use a different notation, for example x3, then this has the form x3 mx3, which is in the set U according to the definition of U, with the value x3, which is x2 plus x1, and it's a real number. So after we described U, we can check, well, we have the very important form of U, that it's these x, mx points or vectors. And now using this form of the points, we can check all the three properties that are needed for U to be a subspace. So the third one is the scalar multiplication for a real number, since we considered real numbers as scalars. Then if you have a vector v, then it has the form x1 mx1 if it's in the subset U. Then for this we write how a times v looks like, and it has the form a times x1 mx1. We already defined scalar multiplication in general in R2, and that's component wise, ax1 a mx1. Well, originally it's supposed to be a multiplying mx1, but then we can simply change the order, since a times m in the real numbers it's commutative, the multiplication. So then we get x2 mx2 form, which is in U according to the definition of U, with x2 in the form of a x1. So that would be the rigorous proof that U is a subspace of V in R2. Next example, for something which is not a subspace, again in R2. Well, we like straight lines, linear functions, so V is R2. Let's consider, for example, the straight line y equals to 2x plus 1. So this is the set U. The easy way to describe it is that the x, 2x plus 1 points, since y is 2x plus 1, with x going through all the real numbers. So why this is not a subspace? If this is not a subspace, then one of the three conditions should fail, or maybe more. One or more of the three conditions will fail. So the three conditions again were that the set is not empty, addition stays in it, scalar multiplication stays in the set. Well, we see immediately that it's not empty, so it's not going to fail, this condition. It turns out that both second and the third conditions will fail. Let me choose one to show one condition to fail, and then maybe I give as a homework the other condition to show. So first of all, 3 fails, scalar multiplication. So the condition was that for all A from the field, for all vector from the vector space, not actually from the vector space, from the set U, we have that A times V stays in U. So if this fails, that means the negation will be true. So we will need to negate this statement that for all A in F, for all V in U, AV is in U. So the way we negate is that we change these for all quantifiers to the existential one. So there is an A in F, and there is a V vector in U such that AV is not in U. That's how we negate it. And sometimes it can be tricky how you find. So when it says something says that exists, then we have to find it. Of course, sometimes it can be tricky to find very special values for which a statement is true or not true. In this case, it's almost arbitrary. So there are, if you have to find special values of a scalar, of course you can try 0, 1. They are special scalars. And then if they don't work, then choose different ones. So for example, A equals 3. And then, so this is a scalar. And choose, or a vector from this set, let's choose 0, 1 vector. So that's in the line. And then let's see what A times V looks like. So this is 3 times the vector 0, 1. This is 0, 3. Then how do we show that this is not in the set U? Showing that this is not in the set U, we can use contradiction, proof by contradiction, to show 0, 3 is not in U. So assume that 0, 3 is in U. Again, U was the set of these points on the line with coordinates x, 2x plus 1. So that means that 0, 3 has the form x, 2x plus 1 for some x. But then vectors are compared component by component. So from here we get x equals to 0 from the first component. And then we have 3 equals 2x plus 1. But substituting x equals to 0, we get 3 equals to 0 plus 1. 3 equals to 1, which is contradiction. This contradiction was from assuming that 0, 3 is in U. That means that 0, 3 is not in U. So with this, we found a scalar A and a vector V from U such that A times V wasn't in U. That means we showed that condition 3 fails. That means U is not a subspace. Another example, vector space of polynomials. Clearly it's a subset. Pn is a subset of Pn if n is less than or equal to m. So lower degree polynomials can be considered higher degree polynomials with 0 coefficients for the higher powers. So we also have that these are subspaces if n is less than or equal to m. We're supposed to go through, of course, checking all 3 conditions. And another example, a little bit more abstract. We the vector space, let's consider to be C01. So this notation will be used also later. This is the vector space of functions, actually continuous functions. That's what this T stands for, over the interval 0, 1. We could also use just the whole real line for the domain of the functions, but I don't like to work actually with infinite intervals. Then a subset U could be considered as C1 of 0, 1 over 0, 1, which is the once continuously differentiable functions considered over the interval 0, 1. All right, and what we know from calculus 1 is that if a function is differentiable, then it's also continuous, but not vice versa. So what we have is that U is a subset of V. It turns out that U is also a subspace. Of V. What we have to see is that the sum of differentiable functions is also differentiable, and scalar multiplication, we have the rule for the differentiation of a scalar product of a function.